When we talk about artificial intelligence, training often gets most of the attention because it is the stage where models learn patterns from data, adjust their parameters, and acquire general competence. But inference is equally important, because inference is the stage where models are actually used. Inference is the process of taking a trained model and applying it to new inputs to produce outputs. It is the moment when the model moves from learning to doing, from absorbing knowledge to applying it. Without inference, training would be an academic exercise. With inference, AI becomes a practical tool that can generate text, classify images, translate languages, or make predictions in real time. Inference begins with an input. For a language model, the input might be a prompt or a sequence of tokens. For a vision model, it might be an image. For a speech model, it might be an audio waveform. The input is pre-processed into the format expected by the model, such as token embeddings or pixel arrays. The model then processes the input through its layers, applying the parameters learned during training. Each layer transforms the representation, capturing increasingly abstract features. At the end, the model produces an output, such as a probability distribution over possible next tokens, a classification label, or a generated sequence. This output is then post-processed into a human-readable form, such as text or a decision. Inference has unique challenges compared to training. Training is performed offline, often on powerful clusters with distributed computation. Inference must often be performed online, in real time, with constraints on latency and resource usage. A chatbot must respond quickly to user queries. An autonomous vehicle must process sensor data instantly to make driving decisions. A medical diagnostic system must provide results promptly to support clinical workflows. These requirements make inference a critical engineering problem. Optimizing inference involves reducing latency, minimizing memory usage, and ensuring scalability. One of the key techniques in inference optimization is quantization. Quantization reduces the precision of model parameters from floating point to lower precision formats, such as 16-bit or 8-bit integers. This reduces memory footprint and speeds up computation, often with minimal loss in accuracy. Another technique is pruning, where redundant parameters or connections are removed from the model. Pruned models are smaller and faster, though care must be taken to preserve performance. Knowledge distillation is another approach, where a large model teaches a smaller model to approximate its behavior. The smaller model is then used for inference, providing efficiency while retaining much of the original capability. Hardware plays a crucial role in inference. GPUs are widely used because they excel at parallel computation, which is essential for matrix operations in neural networks. TPUs and other specialized accelerators are designed specifically for AI workloads, offering even greater efficiency. CPUs are still used for inference in many applications, especially where resources are limited or where integration with existing systems is required. Edge devices, such as smartphones or IoT sensors, often perform inference locally, requiring models to be optimized for low power and limited memory. Cloud services provide scalable inference, allowing models to be deployed as APIs that can handle large volumes of requests. Inference also involves considerations of batching and parallelism. Batching allows multiple inputs to be processed simultaneously, improving throughput. However, batching can increase latency for individual requests, so trade-offs must be managed depending on the application. Parallelism across devices or cores can further accelerate inference, but it requires careful synchronization and load balancing. Engineers must design inference pipelines that balance speed, efficiency, and responsiveness. In language models, inference involves generating sequences token by token. The model predicts a probability distribution over possible next tokens, and a sampling strategy selects one. Greedy decoding chooses the most likely token at each step, producing deterministic outputs. Beam search explores multiple candidate sequences, balancing probability and diversity. Sampling with temperature adjusts randomness, allowing more creative or conservative outputs. Top K and nucleus sampling restrict choices to the most probable tokens or to a cumulative probability mass, controlling diversity. These strategies affect the quality, coherence, and creativity of generated text. Inference is not just about speed but also about controlling behavior. Inference also raises questions of safety and alignment. A model may be capable of generating fluent text, but without careful control, it may produce harmful or misleading content. Reinforcement learning from human feedback is often applied after training to align models with human preferences, but inference must still enforce safety filters and guardrails. This involves detecting unsafe outputs, applying constraints, and monitoring behavior. Inference systems must be designed not only for efficiency but also for responsibility. Evaluation of inference performance involves metrics like latency, throughput, and accuracy. Latency measures the time from input to output. Throughput measures how many requests can be handled per unit time. Accuracy measures how well the outputs match expectations. Robustness is also important, as inference systems must handle diverse inputs without failure. Interpretability methods can be applied during inference to provide insights into model decisions, though this often adds overhead. Engineers must balance transparency with efficiency. Inference is also where personalization occurs. Models can be adapted to individual users by incorporating context, preferences, or history into inference. This allows systems to provide tailored recommendations, personalized dialogue, or adaptive behavior. Personalization enhances user experience but raises privacy concerns, since inference may involve sensitive data. Secure inference methods, such as homomorphic encryption or federated learning, are being explored to protect privacy while enabling personalization. Looking ahead, inference will continue to evolve. Advances in hardware will provide faster and more efficient computation. New algorithms will reduce latency and improve scalability. Hybrid approaches will combine cloud and edge inference, balancing power and responsiveness. Multimodal inference will integrate text, images, audio, and video seamlessly, enabling richer applications. Real-time feedback loops will allow models to adapt during inference, making systems more dynamic and responsive. Ethical and governance frameworks will shape how inference systems are deployed, ensuring that they serve human needs responsibly. In summary, inference is the stage where AI models are applied to new inputs to produce outputs. It involves pre-processing, model computation, and post-processing. It requires optimization for latency, efficiency, and scalability. It uses techniques like quantization, pruning, and distillation. It relies on hardware like GPUs, TPUs, CPUs, and edge devices. It involves strategies for decoding and language models, balancing coherence and creativity. It raises challenges of safety, alignment, and privacy. It powers applications across industries, from chatbots to autonomous vehicles to medical diagnostics. It continues to evolve with advances in hardware, algorithms, and governance. Inference is the bridge between training and application, the moment when AI becomes useful, and the key to making intelligence practical.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.